Hello everyone, welcome back to the module Robot Dynamics. So in the previous class we learned how to derive dynamic equation of motion using Lagrange-Euler formulation. We understood the physical significance of equation of motion terms in context to inertial forces and torques, centripetal and Coriolis forces and torques, and gravitational component of the equation of motion. We learned the limitation of industrial robot, why it doesn't allow much of the equations of dynamics to be implemented while we actually program it. Okay, so however, we'll continue today with one more formulation, that is Newton-Euler formulation, to obtain the joint torque and forces given the motions of the links and the joints. We'll try to get the equation of motion, the one which we obtained just like Lagrange-Euler formulation. So we'll try to get. So let us start. So before we begin, let me just see why do we need Newton-Euler formulation. What was the problem with our earlier formulation? Okay, so Lagrange-Euler formulation equation of motion contains the terms with multiple derivatives. You saw it used partial derivatives with respect to velocity, joint velocity, as well as with respect to time. We also used a partial derivative with respect to joint angle. So you know now it includes quite a lot of derivatives, and there are terms called nonlinear terms, which are Coriolis terms, centrifugal components, that make it computationally inefficient for any real-time robot control, because you need to take the derivatives, and taking derivatives digitally using programming, that is not that computationally easy. Okay, so that is what limits a lot Lagrange-Euler formulation to be used directly in any control system or directly using it apart from doing some sort of offline simulation and all. Okay, so a simplified robot arm dynamics model may be used. We saw dynamic torque is equal to I theta double dot plus C theta theta dot plus gamma theta you saw. So you can ignore the term which is including Coriolis and centrifugal component. So that will make it a little simpler. If we assume that robot is not moving quite fast, we can do that, but yes, that also is possible only for slow moving robot, for animation and all those stuff, which doesn't require much of accuracy in calculation. Okay, and Coriolis and centrifugal components are significant in joint torques when your arm moves really very fast. Normally industrial robots, they run at 2 meters per second. At the tip velocity it goes like that, so it is very very fast, you see. Okay, so at high speed the errors in the joint torques resulting from ignoring the Coriolis and centrifugal forces cannot be corrected because excessive requirement on the corrective joint forces and torques. So let us say you are using a model based control, you are using your dynamic equation of motion without Coriolis and centripetal term. So that is fed to the robot. We are checking the errors. We are further correcting that using our controllers. So that correction goes really very high. And that is sometimes not enough to take care of complete precise control of the end effector. So that is what we'll talk about, these controls and corrections in our control module also. Okay, so Newton-Euler approach allows recursive formulation. We'll see what a recursive formulation is, and programming, it also allows easy programming to obtain runtime variables in real time. Okay, there are limitations to this also, we'll discuss immediately after this. So yes, traditionally Newton-Euler formulation was derived, it used something like this, a link. Link is mounted on a frame which is here, it ends with a frame which goes here. You have seen similar situation in when you were placing frames in your DS parameters. Okay, so you had a frame before to link about which your link is making its motion, and there is a frame which is attached at the end of the link that is actually moving along with the link. Okay, so let us say it is acted upon by forces from the link which is before to this. This is the moment, these are the force. Okay, and similarly this link also applies forces and moments to the link which comes next to it. Okay, so in reaction this also will see this force and the moment. Let us say it has its own angular velocity omega I, and it has the center of mass which is located here, and it has a velocity given by Vci. Okay, this is the mass which is acting due to the center of gravity. This force is coming, okay, that is towards the direction of G. Okay, joint I plus 1. So there are additional parameters which are put here. So with respect to OI, that is the link attached frame, so there are two vectors which are to be noted. One of them is the mass center location with respect to link's own frame, that is given by Ri, Ci. So that is this, and again you have Ri minus 1 I. So what is that? It is a vector that connects this to this. Got it? So with this, all parameters and symbols that I have used, so Mi is the mass of the link, Vci is the linear velocity of centroid of the link I in frame OXYZ, that is with respect to this. Okay, and you have forces given by this, force over here, force over here. Okay, and you have moment, coupling moments that comes on the, that is applied on the link by the links I minus 1 and I plus 1 respectively. Those are here. Okay, and you have moment of inertia tensor. You know moment of inertia tensor, it looks like this. You have principal moment of inertia that comes here, Ixx, Iyy, Izz, and then you have product moment of inertia, Ixy, Ixz, similarly Iyx, Yz, Izx, Izy. So this is your inertia, moment of inertia tensor. It looks like this. These are the product moment of inertia, whereas the terms which comes here in the diagonal, they are principal moment of inertia. Omega I is angular velocity vector, that is here. Okay, so using free body diagram of the link I, you can write this equation. We have written it earlier while we were doing statics. We used till here only. This time this additional term will also come. This is the force acting due to the acceleration of the center of mass, that is this. So if this is the velocity, Vci dot is the acceleration of center of mass. So that is also added on here, apart from this gravitational force. This is the gravitational force. This causes the force due to the acceleration, and these are the forces that is acting on the body. Okay, so these are the two forces. So vector sum of all of them should be equal to 0, because I assume if it is taken care of by accelerating forces over here, sum should be equal to 0. Okay, or this is the set of force which is causing this acceleration. It is either way, it is true. Similarly, when we consider moments from both the directions, both the sides, one is this, another one is this, so those are the pure moments that is coming on the link. And you also see moment that is because of the forces acting on this frame over here and over here. So you know the distances already, so quickly you can call it as Fi minus 1 I, that is acting over here, and you have distance which is given by two vector sum, this and this, that is effectively I am trying to find out this vector. So this vector in this force, that is the moment taken about Ci, and you also see a moment due to this part of it, and that is given by minus Rci, that is this vector, and this force that is here, and you have angular acceleration which is here, and moment of inertia is here. This is inertial moment that will come, so it is given by I omega dot, and you also have gyroscopic moment which is coming here. Okay, so that goes here. Okay, So that is given by omega I cross I omega I. So that is the another term. So you have what all moments that you see? It is the pure moments that is acting on the link, and moment due to the forces, moment due to the inertia of the link itself, inertial moment, that is due to the omega dot, and you have gyroscopic moment. Okay, so that comes here. Okay, so the complete equation of motion is obtained by evaluating both the equations, this equation and this equation, Newton and Euler equations, and combining them together for all the links. Okay, for I is equal to 1 to n. So for all the links, you write these two vector equations, and you can do in a forward and backward manner. So what you do in the forward recursion, you calculate velocities and acceleration in forward recursion. That means if your serial chain looks like this, you have links which are connected like this. So any velocity over here is going to affect the tip velocity. Velocity over here will also affect this. So this is actually affected by any of the velocities which comes prior to this. So you have to move forward. Okay, you have to move forward from here to here. So all the velocity contributions due to the links which comes prior to this is added on, and it goes here. Okay, so we do velocity and acceleration at any joint or at the link mass center. Okay, so that is to be considered by forward recursion. Okay, that is all the velocities which comes before to this is to be considered, and they are contributing to the velocity that comes here. And similarly, the joint forces are evaluated in backward recursion. So we have done this in similar manner while we were doing statics. So again, if your robot looks like this, so if you want to calculate joint forces over here, all the links that comes after this has a contribution over here, but any link which comes before this doesn't have any contribution to the torque that will come here. Okay, so that is the reason it is calculated in the backward manner. So you know your constraints which are acting at the tip, then you know this, and you move like this. Okay, so that is the reason you are moving backward. So using these two pair of vector equations for all the links, you calculate the joint velocities and acceleration, as we have discussed in earlier module also while discussing differential motions. Okay, so you use these equations, and you can do backward recursion to calculate the moments. So moments are projected further along the joints to obtain the torques at the joints. Okay, so joint torque is not explicitly involved in Newton-Euler formulation. So that was there in Lagrange-Euler formulation. You see, each joint you directly obtained the joint torques. Here you don't obtain the joint torque, you obtain the moment, and you have to project that along the axis, that is EI minus 1, EI minus, like that you have to project onto those axes to obtain the joint torques. Okay, so this is a traditional approach of Newton-Euler. Again, you see, you have to write a huge number of equations, you have to substitute a lot, and you have to obtain the joint torques. Okay, let me just move a bit so that you can see the slide clearly. Yes, this is what was there. Okay, so now let us discuss standard moment of inertia. How does it look like? As I have told, so it should look like this. This is simple recapitulation. You just should remember how mass moment of inertia is calculated along x-axis, along y-y, along z-z. So these are the diagonal terms, that is directly giving you the principal moment of inertia, and product moment of inertia is defined like this. Okay, so yes, this is how you calculate the link moment of inertia. This is to be calculated about center of mass of the link. Okay, so anything, if it is in any other frame, you have to bring it to this frame. So bringing it to any frame, you know how to do it. using the orientation matrix of that particular link. So we'll do it and demonstrate it. Okay, so now there is yet another extension of Newton-Euler formulation, which is actually allowing you to calculate this programmatically, recursion, through recursion. If you know joint parameters, link and joint parameters, for one of the link which comes next, you can calculate this one. So using this, you can calculate this. Using this, you can calculate the previous one. Using this, you calculate the previous one. So iteratively, you can come backward, or similarly, you can go forward while calculating the velocity. So that is how, using recursion, it becomes very, very simpler to do programming and formulating these algorithms. Okay, so yes, forward computation. You know this equation very well. Already we have discussed this in our earlier module in kinematics earlier. Okay, in differential motion also we have discussed this. We have taken derivative, we found out velocity, we also find out the acceleration. Again, I am just coming back to that. So yes, angular velocity omega I for any link is given by omega I minus 1. So this is your link, that is ith link. So angular velocity of this link omega I, let me just clean it up. Okay, angular velocity of this should be angular velocity which is imparted by the previous link, because this link is mounted on top of the previous link. So whatever angular velocity that comes due to this angular velocity omega I minus 1, you also have joint angular velocity. You have theta dot, that is here, and that is along ei. So if you multiply this scalar theta dot with ei, this effectively gives you omega I. Okay, so that is over here, that is landing over here in its own frame. Okay, in its own frame. So total omega I, that is the net angular velocity due to this contribution, and the joint angular velocity sum together will give you angular velocity that this Ci sees, or whole of this link sees. Okay, so whole of the link will have angular velocity due to omega I minus 1, that is the on which it is landed on. So there is a link which is mounted on this. So if this previous link rotates, this also rotates with same angular velocity. Apart from that, there is relative angular velocity that is to be added. So that is what is there. And in case of prismatic joint, there is no theta dot. There is no angular velocity. So whole of the second link is mounted on the previous link. If this rotates with angular velocity omega I minus 1, so the next link will also have same angular velocity, because there is no relative angular velocity, there is only linear displacement which is there. Got it? So that is in case of prismatic joint. Got it? Now you know all the vector sums can be done only if they are represented in the same frame. So philosophically it is exactly this, but now in order to do it actually practically, you should understand these representations are in different frames. Okay, we know the values in its own frame. Okay, we have to convert it to the frame in which we are calculating. So in order to do that, you now have to do this. Okay, so what is this actually? This is Qi. You know this very well. Qi minus 1 is rotation matrix subset. Okay, that is a subset of transformation matrix. You know that was, it has 3 cross 3 rotation matrix, and translation over here, this was 1, this was 0, 0, 0. So this was your Q, and that can be obtained from the transformation matrix, you know. So this is your Qi, that is link transformation matrix that takes you from this to this, and this gives you position of this with respect to this over here, and orientation of I plus 1 with respect to I. Okay, if it is Ti I minus 1. Okay, so you got it. So this is what your transformation matrix gave you. So a part of this in case of, so let me just wipe it off. Okay, so yes, this is your same matrix. Now omega I minus 1, that is a link which was connected prior to this. This had a angular velocity of omega I minus 1. Okay, and you have angular velocity over here, that is what you want to obtain, that is omega I. Okay, so qi minus 1 is a 3 cross 3 rotation matrix, you just note it down, that represents orientation of frame I attached to the link I minus 1 with respect to the frame I plus 1 attached to the link I. Okay, so how does this transformation happen? You basically extracted this from transformation matrix I minus 1, link transformation matrix. So you know all these parameters using DH parameter, so you got this orientation directly. So let me just elaborate upon this over here, how this equation came actually. So yes, so let me just draw it once again over here. You have a link which is here. You have yet another link that comes here. Okay, this is your frame OI minus 1, and this is your frame OI, and then you have a frame which is here, that is OI plus 1. So this QI minus 1 is basically give you a transformation that took you from here to here, orientation transformation from here to here. Okay, now you have angular velocity about this link, that is omega I minus 1 about its own frame, you know it is omega I. Okay, so this is given by this omega I minus 1. So that is here. Okay, now you have to represent all these to the frame which is here about, because you want to do everything at this. Okay, over here. So now you have to transform this to this. You know this angular velocity is over here and it is represented over here, but you know the transformation. This is the fixed frame to this link, and you know the location of this, orientation of this with respect to this. Okay, that was given by qi minus 1. When you take transpose of this, that is equivalent to taking invert to this. So inverse of this is equal to transpose of this. So taking inverse actually represents this with respect to this, that is making this frame stationary. This frame is stationary. Now you are looking everything in this frame. So when you multiply qi minus 1 transpose to omega I, okay, this one, okay, you are multiplying this to this over here. So what do? Basically you represent this omega in this frame. Okay, so now you know omega I minus 1 in this frame. So this is now well known, and you already know this link is rotating by theta I dot about an axis in its own frame given by EI. So that again is in this frame, ith frame. So now both of these can be added together. So what I actually did here, I multiplied qi minus 1 transpose to omega I minus 1, that effectively transformed omega I minus 1 to ith frame. Again, this is the relative angular velocity. So total angular velocity in ith frame is omega I, that is seen by this, that becomes omega I in its own frame. Okay, so this is how it works. So now let us go back to our earlier slide. So that is what was given by this. In case of prismatic joint, only this term will be absent. There is no relative angular velocity. So only this part remains. Okay, so now you got what is omega I in its own frame. Now let us move ahead. So this is what you have seen. So now angular acceleration, how does that propagate? Okay, so that was one. This is an recursive relation, you see. If you know omega I minus 1, because you know velocities are done by forward computations, acceleration and velocity. So you have expressed the next one, this one, with respect to this. Okay, so this comes later, this comes prior. Got it? So you have to calculate this from this. Okay, you have to go from bottommost first link to the last link. Okay, so that is how we move. Okay, now moving ahead. Okay, in case of angular acceleration, I did nothing. I simply took derivative of omega I, what we have obtained earlier, and you can directly get to this. If you want, you can just get it to this. Omega I was equal to omega I minus 1 plus theta I dot into EI. This is a vector. This is omega I dot is a scalar. If you take derivative of this, you get omega I dot should be equal to omega I minus 1 dot plus these two are products, so you do theta I double dot EI. This is again along same direction, plus you have theta I dot. Now EI is a vector, so it is not changing in magnitude, so it is changing in direction. And how it is changing? It is given by omega I cross EI. So these are the two vectors. So you see, you have to take cross product over here, and this is there. So this is perpendicular to the direction of EI. So this is along tangential direction, this is along the same direction. So yes, these are the two accelerations. These are the two accelerations that are added to this. So finally, just taking derivative of this, you can obtain the acceleration. Got it? And in case of prismatic joint, all of these will be absent. Got it? So this is quite trivial now, at least. Okay. So again, in ith link frame, the way we did it for angular velocity, we can do it with angular acceleration also. Again, we have to bring everything to the ith frame. We again multiplied with the same transformation matrix. Now that is the orientation matrix, inverse of that, so that it comes to the ith frame. So this equation in ith frame can be written as this. So this again is a recursive relation for computing the angular acceleration of the link I in terms of I minus 1. So you are going again forward. Okay, so angular acceleration and velocities are done. Okay, now the linear velocity and acceleration. So yes, this time again, this is your CI, that is the center of mass velocity I want to find out. So again, this link is riding upon the previous link. So it sees a velocity which is contributed by the, so this is a link, you have a previous link which is here. So how will you do it? You have a velocity over here that is given by CI location. CI dot is its velocity, and you have angular velocity omega I minus 1. So angular velocity contributes to its total velocity. Omega I minus 1 has its contribution over here. Okay, that is CI location, CI dot we want to find out. So over here there is a contribution due to omega I minus 1. So that is given by this distance. Okay, so omega I minus 1 cross Ri minus 1, and again omega I itself will have its contribution over here, that is given by this. Let me just put down all the variables here only. So this is your Ri minus 1, and you have another vector which is di. All these are in 3 dimension. I am just drawing it in planar fashion. This is your Ri that will take you to the next one, next joint. Okay, so this one has omega I, this has omega I minus 1. So yes, if you have to transfer omega I minus 1 to this joint, so you have to multiply with the distance which is here. So Ri minus 1 cross omega I minus 1 gives you velocity that comes here. That is the velocity contribution due to omega I minus 1. This is pure velocity. This is velocity due to angular velocity. Okay. And then you have velocity contribution due to di distance. So this is your di distance and this is your omega I. So that also has got contribution over here. Okay. So overall the total velocity is seen by this. Okay. Now in case of prismatic joint, things are little different. So in this case you have a link, but this time this is your omega I minus 1. This again is your Ri minus 1. This is your joint, but this joint this time has got a prismatic extension, and then comes your link that comes next. It may be rotating again, it may be another prismatic joint. Forget about it, but yes, this is your center of mass location of link I. This is Ci minus 1, and you have few things over here. This is your joint offset. This is Bi, let us say it is along Ei joint vector, okay, axis vector. So this is your Bi. Bi is the joint offset. That is what is changing. In case of prismatic joint, you know, that is not constant, that is extending or it can retract. Okay, so Bi is a joint variable. There is no theta I here. Okay, and then you have Di that comes here. So now you can understand. So when you want to come to this joint, so what all velocity contributions that will come here? It is 1 due to the pure velocity of the previous link, because this link itself is riding upon the previous link, so it is given by Ci minus 1 dot, and now due to the angular velocity contribution. So total angular velocity omega I minus 1 is at a vector distance of Ri minus 1 and Di from here. So that is directly added over here, and cross product of that will give you velocity, linear velocity due to omega I minus 1, and pure velocity component due to this Bi dot and Ei will also give you some velocity. So that is coming here. So total velocity is this. So in case of rotary and prismatic joint, it comes like this. Okay, you have to draw your own figures, better figures. Maybe you can draw in 3 dimensions somewhere in CAD, join the vectors and see how does it look like. Put all the variables clearly and you can see it. Okay. So yes, hope it is quite clear so far. It is not more than engineering mechanics once again vectorally. Okay, and yes, I am using matrices over here again to convert everything to link frame, ith link frame. Okay, again you have to multiply with Qi minus 1 transpose. It is inverse actually. So where in case of prismatic joint it was like this. Again I have taken derivative of, yes, this is exactly the same. So omega I in its own frame is this in case of prismatic joint. So in case of prismatic joint it is very trivial. You know that we have just carried it out from the previous slide. Okay, now what are these parameters? So what is this? This is basically AII, that can be written as, we have written it earlier also. So AI cos theta, AI sin theta, and theta is actually the joint variable. Okay, and Bi is again the, in case of prismatic joint, Bi also is a variable, but it may be a constant in case of rotary joint. So this is AI vector, that is the vector which connects OI to OI plus 1 at frame in case of link. Okay, OI minus 1 to OI or likewise. This is Ri vector. So Ri has got 3 components. Those are put as Rx, Ry and Rz. Okay, so this is again a recursive relation for computing linear velocity of the link I in terms of link I minus 1. Okay, this is link I minus 1. Got it? So this is done. So this is linear velocity contribution. And then finally you have linear acceleration propagation. I did nothing. I simply took the derivative of earlier equation and I got to this. Okay, this includes everything. If it is a vector, it has to be if it is not changing, vector can change in two number of ways. First, due to the change in its magnitude and change in its direction. And direction, if it is changing, you have to take cross product with the direction. So that is what is done in over here. Because the Ri, if you take cross product of omega and r, so either omega is changing or r is changing. Again, if r is changing, r can change in two different ways. So r can be just change, it can just change like this, or it can take this form. Okay, so that is what is to be understood first. Okay, so r can change either directly by changing the magnitude of r or by changing the direction of r. These two are independently given like this. So you have to take derivative accordingly. So all the parameters which was seen over here is to be considered that way. So this is the term which I am talking about. So you have to take derivative of r in two times. First r dot will come, next time you have another omega cross r. Okay, so that is what is here. So you have omega dot r, and when you have to take this, so you have to take omega cross r, that comes once again. Okay, so r dot, because you know r is a constant term, so r dot is not existing, so you only see omega cross r. Same over here. In case of omega and d, you again did, you know d is constant, so it is this. So this is second term. So that is how it is done. And in case of prismatic joint, you have b double dot that will come, and this is two times because one of them has arisen due to the derivative over here. So overall, this is the linear acceleration propagation. Again, this is to be put in terms of ith frame. Okay, everything is to be put in ith frame because we have to conclude with ith frame first, then we have to do recursive calculation. So every time we move forward, calculate the ith velocity, I plus 1, I plus 2 till n. Okay, these are all the recursive relations. So if you know omega I minus 1, you calculate omega I. If you know ci minus 1 double dot, so you can calculate ci double dot. Got it? So you have to move forward that way. So you are moving from I minus 1, I finally up till n. This is how you are moving recursively in the forward direction. So accelerations, velocity is to be done like that. Okay. So this is how linear acceleration is also done. Okay. So we are done with all those. So now acceleration due to gravity is also be converted to ith frame. So you again have to use the same transformation matrix. That is the orientation matrix change. Okay, so that is how it is done. G is consecutively changed from previous frame to this frame. Again, this becomes the previous one, next one will come. Okay, that is how you keep moving from 0 to, this starts from 0, that is the ground frame, and now it gradually moves till the end effector frame, that is the last frame, link frame. Okay, so that is how G also is converted to the ith frame every time it is considered for that particular link. Okay, so that is how in 5 steps you did all with velocities and acceleration and G. Okay, now we'll use backward computation. Now that I know all the angular velocity, I know all the linear velocities and acceleration, you know omega, you know omega dot, you know c dot, and you c double dot also. So you have all the velocities and acceleration in hand while doing forward computation for all the link. Now you go use these calculate the forces and moments. So force is nothing but mi ci double dot, mass into acceleration of that. Similarly, moment will be this term. This is an additional term. You know it is gyroscopic moment that is going to come. So that is also considered here. So in terms of recursive relation, this two fundamental equation that we have done earlier also, so that is to be used. This was a similar equation that we have used over here. I'll just show you here. So this is a similar one when you have converted the equations, previous force, this force, mass and velocity, acceleration forces. So all the forces are here, all the moments are here. It is exactly a similar equation. Okay, but yes, this is a recursive thing that we want to discuss. So you see, terms are very similar. This is again two forces that is acting on the link. This is the link own force due to the gravitational force that makes the total force. Similarly, moment is because of the moments that comes here, that is formulating final moment that is over there. These are the forces that are causing the moment on this link. Okay, so total moment and total force is something like this. So it is again a recursive relation. You see, it moves in a backward manner. This time it is in a backward manner. This time again I'll tell you. So if you have arranged in a recursive fashion, so what effectively you did, you have to arrange it in a backward manner. So this time, because you know this can be computed because you already know the terms which are before to this. So all the terms are rearranged in recursive manner. This time you know already this, so you can calculate the previous one. So this time, if this is the link, this is the link, this is the link. So effectively you start from here where you know the forces that are acted here, that are acting here, and then you calculate at this step adding this gravity component. Okay, you use this and calculate this, use this and calculate this, use this and calculate this. Not just the gravity component, there are other components also that will come. Okay, so that is what is contributing to this. So finally you are calculating in the backward manner because you know everything at the end frame. Okay, so that is why you are moving backward. So I have rearranged the same force and moment balance equation in this manner. Okay, now you know most of the terms. Okay, so backward way. And finally, when you calculate all the moments, you project them to using EI vector. EI vector can be extracted using link transformation matrices, that is using forward kinematics, and you can project all the moments to the link joint axis vector, and you get the torque along that axis. Okay, so tau I is the last element of the vectors. These tau I is again, in case of revolute joint you have to use this and project. In case of prismatic joint, this is converted to a force that is acting on the prismatic joint. Okay, so this is how in 7 steps you do all the recursive calculations. Let us quickly see one example here. So this is just a single link manipulator. Recursive, you will use recursive Newton-Euler formulation to do this. So this is the joint. I have assumed x directed downwards, that is along G, which is shown here, x1, y1. 2 is the frame which is at over here. So there are 2 frames only. So about first one, the link is moving, and link is moving with, okay, so the second joint which is placed on top of it. There is no second link. So this is the tau I want to obtain. Okay, these are the forces, reaction forces that acts over here. So I have just isolated them. I will just check what are the forces that are going to come. Okay, so this is the transformation matrix. This is nothing but expressed as frame 2 with respect to frame 1. This is nothing but rotation about the z axis, which is perpendicular to x1, y1. So that is rotation about z axis is given by cos theta minus sine and cos. 1 goes here. This is the orientation matrix of this link. Okay, of that will represent frame 2 with respect to frame 1. This is AI in first frame when it is represented in first frame. So if this is link length A, so link length A can be represented as in first frame as A cos theta, A sin theta and 0. These are nothing but components along x, component along y. So cosine goes here, sine goes here, and 0 because it is a planar system. Okay, so these are some variables that I quickly obtain. Again, assuming the links to be homogeneous, I am assuming this link is has uniform mass and it is slender and mass is uniformly distributed all over. So center of gravity is exactly in the midway, somewhere over here. This is your C1 location. So yes, D1 and R1 can be given as this. Okay, so you know what are they? So this is your D1, this is your R1. So again they have to be represented in different frames. You know, so this is nothing but A1 by 2 should give you D1. So it is D1. Similarly, R2, is it in its own frame? That is in link frame itself. So it is A by 2. There is no cosine and theta because it is a constant. So it is A by 2, 0, 0. That is, there is only one variable, that is A by 2 along that direction. So that is the only thing that it can see. This is D and R. Okay. So yes, so what is the, assuming this link to be a slender square beam, exactly a thin beam, very thin beam, product moment of inertia will be absent. You will only see moment of inertia of this link along its y-axis and z-axis about x. So link x-axis lies along this. So because it is slender, there is no moment of inertia along that. Got it? So it will only have moment of inertia which are orthogonal to this along these two directions. Got it? This is y and this is z. So and that is given by ma square by 12. You know already, moment of inertia of a thin cylindrical slender bar about its center of gravity is given by this. So that is I. So all product moment of inertia is 0. Moment of inertia about this axis x is 0. So this is the principal moment of inertia that remains. So this is what is your inertia tensor can be written as. Okay, so you have obtained this many variables. Now omega. Omega in its own frame can be written as, okay, omega 1 is nothing but 0, 0. There is no rotation about x and y. There is only rotation about z axis. So it is theta dot, and you know it is theta dot, rate of change of joint angle. Again, omega dot, that is angular acceleration, is double dot of that. That's it. And now the velocity. So you already know what was your position. So you already know the location. So you can directly take derivative of that. You can obtain Ci dot. Okay, so I did nothing. You already know that location. It was A by 2 cos theta, A by 2 sin theta and 0. So this was your C location, okay, in first frame. So this was there. You just take derivative of this and you can obtain this. Got it? And again, acceleration is nothing but derivative of this. I could obtain this. So this is your acceleration of center of mass, Ci. In this case, it is C1. Okay. Acceleration due to gravity in first frame, again it is along x-axis only. You know, x was like this, y was like this. So it can be written like this. So actually I didn't have the space. Can be written as z0, 0 like this. I can write transpose like this. Okay. So this is how G is there. Now using backward computation, you are done with all the forward computation. Now I have to find out the forces and moments. So because this link is a terminating link, there is no link that comes after this. So this makes this two forces and moments equal to 0. That comes from the link which comes after this. So that is equated to 0. Now force is simply mass into the acceleration which is there. So the acceleration, you know, it is exactly this one. So this goes inside, that comes here. So that is the force. Okay, and the moment. Okay, and the moment is again I theta double dot. Okay, so I have simply used this to obtain this. Okay, again if you write it in vector format, you can write it like this. So vector f in first frame can be written as, so you just take ma by 2 that comes here with this only. So that goes here, and along x you also see there is a force which is added here. Okay, that was along x. So net force which comes here is due to the acceleration which is here, that is given by this acceleration, top row, and due to the gravitational pull. Okay, so total force. Similarly, along y direction, you see it is only due to the acceleration in that direction that comes here. There is no acceleration along z. So this is your force. Again, moment, you know there are no moments along x and y. It is only due to this. You have converted that, because moment of inertia was about its center of gravity. Now it is about the tip. So you have to do that transformation and you can obtain this. Okay, so that transformation is done using parallel axis you can do, or you can simply use matrix transformation to do this, obtain this. Moment of inertia can be transformed. Okay, q transpose you can do, and you can do it. So that way you can do this is equivalent to doing parallel axis theorem, applying parallel axis theorem, and this is the added torque due to the gravitational pull. So this is the net torque that acts at joint 1. Okay, so that is the force, this is the moment. Now the torque computation, because this is a revolute joint, it is only the torque that matters. So you just project this to vector, a vector which is here. In this case it is ei is equal to 0, 0, 1 only, that is only first joint you have. So you just project this using this, take dot product, and you can just get this. So adding these two you can obtain ma square by 3, and this remained as it is. So this is the scalar torque that is acting at the joint 1. Okay, so this is how it is applied. So with that we'll end today, and in the next class I'll just discuss dynamic equation of motion of a two-link manipulator using Newton-Euler approach again. Vectorally we will see. Okay, so that's all for today. Thanks a lot.